Hello everyone, I'm Yuxuan Zhao. I'm glad to be here to show my presentation. The subject of my presentation is cloud performance variability prediction. Okay, let's start. So why do we care about performance variability? The answer is that it's helpful for both operators and users. For operators, it can help them to know their facility better. For users, it can help them run repeatable experiments. Previous work identified three kinds of performance variability. They are stochastic variability from noisy neighbors. Well, it was not included in our dataset because our dataset was collected on bare metal machines. The second one is per interaction with cloud provider policies. The third one is cloud performance change points. So what is change point? A change point is a moment in time when static properties before and after it differ considerably. Well, we could have a look on this graph. The right line represents a change point, and before it, the mean of the data is around 1, and after it, the mean of the data is around 5. So there is a mean shift. We could see there is a change point here. In this paper, we made two contributions. First, we use breakout detection to achieve comparable results to change point detection with RobSec. Both of them are change point detection method, and there are many change point detection methods nowadays. RobSec is robust segmentation. It was called by their authors, and RobSec is how I'm going to refer to the method in this presentation. Second, we present a method for predicting performance variability given by change points. And we use gradient boosting model to predict in time when a change point would occur. And we show that our selected method perform well and our confidence level is high. So let's move to dataset. Our dataset was collected over a period of 2 years and 9 months. It measured CPU, memory, and disk performance. And in total, we have 6.9 million measurements. And it was collected on more than 1,600 bare metal machines, as I mentioned before. If you have more interest about CloudLab and dataset, you could have look on these two papers. First, taming performance variability, and it's about long-term performance analysis. The second one is the design and operation of CloudLab. It was about cloud computing testbed itself. So let's come to Changepoint Collection. At first, we use RobSec method. It involves a parameter called threshold K, and it related to magnitudes of potential change points and the ratio of the signal to its standard deviation. In short, it controls how sensitive the detection is. And on this table, we could see that we collect change points in CPU, memory, and disk dataset, and we tried different values for parameter K from 0.3 to 1. And as we can see here, with parameter K increasing, the number of change points increases as well. In the end, we collected 2,000 CPU change points, more than 10,000 memory change points, and more than 1,000 disk change points. The second method we use is breakout detection method, and we tried different values for mean size. We tried from 10 to 25, and the mean size is a minimal number of observations between change points. And as we can see here, with the mean size decreasing, the number of change points increase. And in the end, we collected more than 11,000 CPU change points, 32,000 change points, and more than 8,000 disk change points. Compared with RobSec, we could say that breakout detection is a fine grained, and because it's collecting more change points than RobSec. Here is an example of the comparison between change point detection with RobSec and breakout detection. The figure above is about breakout detection, and the figure below is about change point detection with RobSec. On the graph, the horizontal axis represents the timeline, and the vertical axis represents the execution time, which is a performance indicator of a CPU test. We could say that the red point here represents the data point in our experiment, and the graph shows that the performance of the same performance test run over and over again on the same machine. The changes here are due to the changes in the used version of operating system. And here, blue lines represent change points detected by breakout detection. The green lines represent change points detected by RobSec. We could say that we can tune breakout detection to achieve comparable results to change point detection with RobSec. Okay, let's move to prediction method. We regard this problem as a regression problem, and the output of the regression is when a change point would occur. In this paper, we used gradient boosting models. They are XGBoost, LetGBM, and CatBoost. In the training and prediction process, we use 5-fold cross-validation to avoid overfitting and random search to get a better prediction result. We use root mean square error as our matrix. Okay, here is the prediction efficiency. The table is about the runtime of change points, CPU, memory, and disk performance of one test run. And as we can see here, the runtimes of LetGBM are less than 1 second, and most of these runs take less than 1.5 seconds. It indicates that it's possible to perform these analyses efficiently. Here are prediction features. So the left one is the feature importance of memory change points, and the right one is the feature importance of disk change points. And we could see from these two figures, the left one, the features from memory are OS release, GCC version, and kernel release, etc. But for the disk, the features are disk size, I/O depth, and disk model, etc. So the features from different data sets are different. So what is feature importance? Feature importance is the impact of the features we consider for the prediction of change points. So from these two figures, we could see that OS version changes give rise to memory change points mainly, and for disk, there are many features contributed to disk change points. And that's one of the reasons why the accuracy of the disk prediction is not very high. So how good is our prediction? As I mentioned before, we measured RMSE between prediction and reality. And these are two tables for the performance of our prediction method. We could see here, we get a 4.51 days RMSE for RobSec, and more than 11 days RMSE for breakout detection method. And from these two tables, we could see that our prediction method gets remarkable results in predicting change points for CPU and memory. For example, we could see here, the RMSE is around 5 days. That means there is a 5 days gap between prediction and reality. And moreover, we could say that prediction method achieve a lower accuracy in detecting breakout detection change points due to breakout detection is fine-grained in detecting performance change points. So in the end, let me make a conclusion. First, change points on different cloud resources depend on different factors. Second, change points for CPU and memory can be successfully detected. Prediction accuracy is good for CPU and memory and is comparable for all the methods we tested. Will we get a 4.51 days RMSE with less GBM on memory dataset collected by RobSec? The last change points can be predicted less accurately for breakout detection due to breakout detection is fine-grained. So that's all about my presentation. Thanks for your attention.